Okay, hi guys, welcome back. So we've just concluded the geometric optics section, and I think for the life science-based course, many of you in this class are not quote-unquote physicists, which is totally fine. So I wanted to put the geometric optics unit first to make sure we had enough time in the course to cover it, because whether you go into medicine or whether you go into chemistry or research or pretty much every avenue has optics in it somewhere, whether it be using microscopes or lenses or some sort of manipulation of light. So I put that first to make sure we had enough time. So, please understand that, even if you are going to med school or you think you're going to med school and you're like, well, I'm never going to need this. I'm just taking it because I need it for the MCAT. No, you're wrong. There's a lot of optics in medicine. There's a lot of imagery that goes on. I mean, even MRI machines is a type of electromagnetic radiation, and electromagnetic radiation is light that our eyes cannot see. So, I mean, there is a lot of optics that goes on in medical imaging, and it is beneficial for a doctor to have a better understanding of kind of what the instruments and diagnosis instruments are doing. It better allows you to kind of figure out and interpret the results of some of these tests. So anyway, whether you appreciate that in the moment now or you will become appreciative of it later on in your studies, I will promise you eventually you will be appreciative of it. It's just a question of when. So please understand that it is trying to be in your best interest. Now, moving on, back to something more physics-y, and I will admit this chapter is probably not going to be something most of you will need in your education ambitions. However, nonetheless, it's pretty cool. So it is very useful in the real world, perhaps not to medicine, but cool nonetheless. So we're going to investigate the wave nature of light. Now, as you might remember from high school and possibly even chemistry, depending what they teach now in chemistry these days, light is what we refer to as either being a wave or a particle. We call that wave-particle duality. And when light is behaving like a particle, we call it a photon. And when light is behaving like a wave, we just call it a wave. So there's sort of these two branches of analysis of light. And the one is the particle analysis, which is more so the quantum interpretation. And one of them is the wave interpretation, which is what we call the classical interpretation. So we're not going to be touching on quantum physics in this class. We do talk about it in the calculus-based physics course, Physics 146 and 147. I think downtown that's 151 and 152, I believe, if I'm not mistaken. So we do cover modern physics in those classes, but here we're only going to be talking about classical physics. So as cool as light is, even as a wave, it gets even more cool when you talk about it as a photon, but we won't be talking about that here. Anyway, so first thing we're going to talk about, Young's double slit experiment. So here's the cool part. If a light wave strikes a screen that has two slits in it, what will somebody see? Now, if you think of light as a particle, then and not as a wave, then if you bombard a screen with particles, then many of the particles will just get blocked. But the particles that happen to collide, come on. Oh, now I can't change. Okay, let me minimize, bigger, change color, there we go. So if you have a light particle that collides with an open slit, then you would predict that this would all be dark. This would all be dark, but what would be illuminated is the anti-shadow of the rectangle. And this is what you would predict, and I guess there would be two of them because there are two slits. So this is what we would predict as what we would see if light was behaving like a wave, like a particle, right? Because if you throw a ball through a window, the ball is just going to go straight and then hit the wall in the back. And if light is acting like a ball, then when light hits that screen, it will illuminate the screen. However, this is what was really confusing about, well, why today in 2020 we're still talking about Young's double slit experiment. Even though back when this experiment was taking place, they knew about the sort of wave particle duality of light. This experiment was actually done because they were seeing, hey, look, if light is in fact a photon in a particle, we should be seeing this. And Young's double slit experiment was actually designed to confirm the quantum interpretation of light, like the packet nature of light. And in fact, it proved the exact opposite, which is kind of hilarious. And it really reminds you that science is not, like science is an experimental thing. That, you know, you can theorize about it all day long, that at the end of the day, you need to do it. You know, that's what science is all about. You need to confirm it in reality. And this experiment is actually a hilarious example of that, is where they went into the experiment thinking they were going to provide evidence to support the quantum interpretation of light. And in fact, they ended up doing the exact opposite. They confirmed, reaffirmed the wave nature of light. So in reality, what they saw is now, many striped lines it's a bit of an over exaggeration, but yeah, bright dark bright dark bright dark bright dark, and then everyone was just puzzled. They're like, what? We only have 2 slits here. How is this even possible? Moreover, what was weird is the bright spot that was happening right here was actually in between, oh, that looks like I'm pointing to the top slit. I'm not. That bright spot in the middle corresponded to the region of space in between the 2 slits. So that was even more confusing for them. They're like, okay, seriously, what is actually going on? So here's what's happening. This phenomenon can be readily explained if you think of light as a wave. So if you think of light as a wave, like an oscillatory wave, kind of like a water wave, if you will, in fact, you actually see this exact pattern in water waves, which is the extra weird part. You picture, let's say you shine a light from a flashlight or what have you on a screen, and the screen again has 2 slits. Then what you're doing is you're blocking most of the wave. However, you are letting part of the wave through. So when the wave is traveling through the opening, it's still a flat line. Now, when light, or when a wave, whether it be a light wave or a water wave, passes through and now has the ability to sort of spread out, then it will spread out radially. And you know this is true. When you turn on a light bulb, it throws light 360 degrees. It throws light radially in a circle, right? So when it allows, like here there's a wall. Let me maybe make the wall a different color. Oh, blue on blue, of course. Yeah, that was smart, me. Okay, go me. Okay, so when there's a wall here, you obviously are preventing the light wave from spreading out radially because there's a wall. But as soon as it passes the wall, you allow it to spread out radially, and then it does that. It does exactly that. So when it passes the wall, you know, it spreads out as much as it can over time. And obviously, the longer it travels, the more it spreads out. So really what you're doing is you're turning one light source into 2 light sources. And the second opening here acts in a very similar way, in that it's another source of waves that are starting out small and spreading out as they propagate forward. So what's happening here is you have superposition. you have superposition, and we've talked about this notion before. We talked about it in Physics 136 when we talked about oscillations and waves and sound waves and beat frequencies. We talked about superposition with electric fields, how you can have an electric field and electric field superimposed. We talked about superposition with magnetic fields. So the concept of superposition has been a reoccurring one in physics. And I mean, literally picture a water wave. It's the same idea. So here, what happens is when the crest of the light wave meets a second crest of the light wave, they superimpose and they become extra big, or in terms of light, extra bright. All right. So you'll see here that all the way down the middle, this is the middle here, all the way down the middle, they're going to intersect with each other in a constructive way, superimpose, and then here you're going to get a really bright spot. Okay, so that's how you get a really bright spot in the center, even though it's lined up with what you would expect to be a shadow. Even though it's not a shadow, it's now a bright spot. So that's something super cool. Now, the opposite is also true. Superposition works in the opposite direction as well. When you have a trough, this is it's like an antinode but in the opposite direction. So really what this is here is like when you have a wave, let's see here, blue maybe. Right? So this location right here is where you have one wave that has a maximum in one wave, but a minimum in the other wave. They're both an antinode, but they're opposite antinodes. So they perfectly cancel out. So this would be a dark spot, because you'd have a light wave upwards and a light wave downwards, and they perfectly cancel out. So this would be a really bright spot, but everywhere along here, you would have a dark spot. So you end up getting bright, dark, bright, dark, bright, dark. And that's exactly what we see here. We see bright, bright, dark, bright, dark, et cetera, et cetera, et cetera. So what we see in the actual viewing screen when we do this experiment in real life, as weird as it looks, it's actually very readily explained using wave interference. It's the same principle we saw with sound. Okay. Now, let's do an example. This is not quite, hold on, let me make this a little bit smaller. Why won't you shrink? Come on, why won't you shrink? All right. Okay, so it's not quite a double slit question, but it's a question that sort of gets our feet wet, so to speak. It sort of introduces lambda, and it gets us sort of back in the mode of using waves again. So we'll build to an actual Young's double slit question, but for now, let's just get our feet wet. So in the figure, a light wave is traveling along ray number 1, and it reflects once from a mirror, and a second light ray, ray number 2, reflects twice. It hits the same mirror as before, and then it bounces back and it hits a small mirror fixed a distance L away from the big mirror, and then it is forced to reflect back to this mirror and then back away. Okay, and then the question says the waves have wavelength lambda and are initially exactly out of phase with respect to one another. So if they're initially out of phase, then let's say ray 1 will look something like this. And if they're out of phase with one another, then that means the other ray, actually, let me label this with blue. This is ray 1. Out of phase means ray 2 would look like this. That's what out of phase means. It means if they were to be combined, they would be completely nullified and they would black out. In phase means when one ray has a maximum, the other ray has a maximum. When one ray has a minimum, the other ray has a minimum. Out of phase means the opposite. So we're saying the waves they both have wavelength lambda. However, they are initially out of phase with one another. What are the smallest, second smallest, and third smallest values of L divided by lambda that would result in the final waves being in phase? So again, just for context, let's figure out what's happening here. That says you have ray 2 and ray 1 initially are being shot at the same mirror and they're out of phase with one another. So if you were to shine them separately, you would be able to see them separately. But if you were to shine them overlapping with one another, they would disappear. Again, it's an optical illusion. That's kind of really cool, actually. So that's what that is saying. Now the question though is, here, this travels an extra long distance compared to ray number 1. And if they travel a different distance, then by the time they meet up again at the end, they might be in phase, they might be out of phase, they might be somewhere in the middle. It really depends. So the question is, where do we place our mirror to make sure that the result is in phase? So here's the thing. How do we get the, let's say the red, well, let me draw red in red. How do we get the red wave to be in phase with the blue wave? Well, simply, we shift it. And you see here that in order to get it to be in phase, we have to take the red wave and move it to here. So if we were to shift it, if we horizontally shift the wave, we have to shift it all the way to here, and then the two waves would perfectly line up. Okay, and then they would perfectly line up. So what is that distance? If they're initially out of phase, then we know these two things line up. How far do we have to move it to get them to be in phase? How far is that distance right there? Well, we know peak to peak is lambda. This isn't peak to peak. This is peak to anti-peak. So that distance there is half of a lambda. So if we were to shift the red wave half a lambda, we know we would get it to be in phase. Now, it doesn't have to just be half a lambda. It could be any multiple of half lambda. So it could be 1.5 lambda, it can be 2.5 lambda, 3.5 lambda, 4.5 lambda, 1.5 million lambda. As long as it's like a whole number of lambda plus half a lambda, you know you're going to be shifted in phase at the end of it. So that's really the goal here. So what we need here is we need R2 to travel a half lambda farther than ray 1. That would be the smallest, is a half lambda. The second smallest would be 1 plus a half lambda, or 3 lambda over 2. And the third smallest would be 2.5 lambda, which would be 5 lambda over 2. So that's what we're looking for. What values of L over lambda result in the waves being exactly in phase? Well, like I said, the path difference here to travel farther, the path difference between ray 1 and ray 2 is going to be 2L. Ray 2 travels a distance of 2L farther than ray 1. Ray 2 travels this distance. Ray 1 travels this distance. Ray 2 eventually will travel backwards. Ray 1 will eventually travel backwards. But the thing that ray 2 does that ray 1 does not do is it travels to the mirror and then back again. So it travels L to the left and L to the right. That's a 2L more than ray number 1. So that distance has to equal lambda over 2. And if you solve, the question saying, well, what's L over lambda? If you solve, L over lambda is going to equal, let's see here, 1 over 4. That's the smallest. Now, as I said before, any whole number of lambda plus half lambda will give you the same result. So you could have, this is the answer for part A. For part B, you could say, okay, well, 2L is going to equal 1 plus half lambda. So instead of moving it over once, you'd move it over to this guy, over to here. That would also give you the same result. So this is going to be 3 over 2 lambda. And if you solve for L over lambda, you are going to be getting 3 over 4. And then part C is a very similar thing. Instead of 1 plus a half, it would be 2 plus a half lambda, which is going to be 5 over 2 lambda. And that means L over lambda is going to equal 5 over 4. Okay, so assuming we have lambda, like, you know, we're using red light. Red light would have about maybe 700 nanometers of wavelength. We'll talk about that later on, so I know I'm just kind of dropping that bomb on you, but anyway, if you had lambda, you could reverse engineer what L would have to be, and then that's a way for you to manipulate these light sources to be either in phase or out of phase. So this question is sort of building on what it means to superimpose. This question really illustrates this example here. This example here really illustrates the underlying concept of what's happening in Young's double slit experiment. It's really underlining what it means to superimpose, what it means to be in phase, what it means to be out of phase, and how to manipulate that. Okay, now let's look at some math. Well, in the notion of in phase and out of phase, we learned in the previous example that what's important here is the path difference. The path difference to be in phase has to be an even multiple of lambda, 1 lambda, 2 lambda, 3 lambda. To be out of phase, it has to be an odd multiple, not odd, a decimal multiple, like half, 1.5, 2.5, 3.5, 4.5, 5.5 multiple of lambda. So let's see kind of what's going on here. You have a light ray or a light wave that's coming in from the top one, and then you have a light wave that's coming in from the bottom slit. And if they're meeting at the location that's the center here, then what's the path difference? What's the distance the top ray travels compared to the distance the bottom ray travels? Well, it's the same. They're both not traveling straight. They're both kind of coming in and then bending and then, you know, forming an not equilateral, an isosceles triangle, so to speak. So each side of that triangle will have traveled the same amount of distance. Now, that means there's no path difference, which means they're in phase with one another, which means they're going to constructively interfere and form a bright spot. Now, what if that's not the location of interest? What if you're interested in a location way up over here? Well, for light rays to travel there, then the top ray would go straight there. The bottom ray would go straight there. However, this is no longer an isosceles triangle. Well, I think they call it scalene, that it's nothing special. Here you see that the bottom one has traveled an extra amount of distance. So the way you figure that out is you connect these two waves such that you create an equilateral triangle, not equilateral, isosceles triangle. Right, so now these two are the same. Oh, that's red, let me just use green. Those two are the same, but you're chopping off a little bit of the path. You're chopping off this much of the path. And that represents the path difference. That is exactly how much extra distance the bottom ray has to travel in comparison to the top ray. If that extra distance is a multiple of lambda, whether it be 1 lambda, 10 lambda, 100 lambda, if that path difference is a whole number multiple of lambda, then yeah, the waves will be shifted with respect to one another, but they'll be shifted so they're still in phase with each other. So that's really the important takeaway here. So this is going to be a bright spot when the extra distance is a whole number multiple of lambda. Now we can do the same analysis where if the extra distance is not a whole number multiple of lambda, specifically if it's out of phase, we know it's going to be a 0.5, like 0.5, 1.5, 2.5, 3.5, whatever. If it's 0.5, then they're going to be perfectly out of phase with one another, and then you're going to get a dark spot. So that's what leads to the bright, dark, bright, dark, bright, dark. Now, remember when I said to you that was a little bit idealized, that it's not really bright, dark, bright, dark, bright, dark. It's kind of like bright, less bright, then dark, and then less bright, and then bright. The reason for that is, and you might be wondering here, but Mark, this is not a discrete function. You know, this is a sliding scale. What happens if the path difference is not 0.5 lambda? Or what if the path difference isn't exactly 1 lambda? What if the path difference is 0.35 lambda? Or 0.75 lambda, 3/4 lambda? You're right, that's totally possible. And not only is it possible, it happens. It's a continuous function. So in that case, it's sort of a mix. It's not totally dark. It's like partial cancellation. So you don't get like a totally dark spot. You get like a faint spot. So what you actually see in real life is not bright, dark, bright, dark, bright, dark. It's bright, faint, dark, faint, bright, faint, dark, faint, bright, faint, dark, faint. Because in the middle, the transition, you don't get perfect cancellation or perfect superposition. You get kind of a mix of both. Okay, so hopefully this path difference notion is becoming a little bit more clear now. Before we move on to the next slide, let's figure out how to talk about the path difference or measure the path difference. Well, we know it can be known what this distance is. You know, we're the ones creating the double slit. We're the ones cutting holes in the paper. We're the ones, you know, whatever. So absolutely, we can measure this distance, no problem. That distance there is actually the hypotenuse of that triangle right there. So we say the path difference is this side. Let's call this the opposite side. Let's call this the adjacent side. And then if we introduce an angle, which again, how the hell are you going to know this angle? Well, that's a good question. But we do know that if you are able to measure that angle theta, then that's going to equal the path difference. divided by the slit width, delta D, or D. Okay, so we're well on our way. This means that if the path difference, so if you rearrange, you're going to get path difference equals d sine theta. Again, the theta, you might be thinking to yourself, well, how are you going to measure that theta in real life? I agree. Calm down. We'll get there momentarily. We need to do a bit of an approximation, but we will get there. But I understand that theta is a bit of a cumbersome thorn in your side at the moment. But anyway, that means that this path difference, which is equal to d sine theta, we also could possibly equate it to m lambda, right? If the path difference is a whole number multiple of lambda, then we're going to get a bright spot. Or there's an or if the path difference, oh, let me keep this in a, there we go. If the path difference, or d sine theta, is equal to m plus a half lambda, then we're going to get a dark spot, as we said before. So that's what these equations are saying. These equations didn't come out of nowhere. They're nothing to be confused about. These equations stem from perfectly sound logic. It's not even a rigorous physics derivation, quite frankly. It's a combination of logic and geometry. So I wouldn't even, there's no fundamental laws of physics that this stems from. It's not like conservation of energy, momentum, blah, 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 blah. It's simply, what does it mean to be in phase and out of phase in conjunction with the geometry and quantifying the path difference. Okay, so it's not a super rigorous derivation by any imagination. So this is how you can predict the bright spots, and this is how you can predict the dark spots. Okay. We will come back to theta momentarily, I promise. For a given wavelength lambda, what is the maximum slit width for which there will be no diffraction minimum? And you might be thinking to yourself, okay, well, there's lots of quote unquote slits that you've seen in your real day-to-day life. For instance, a doorway. A doorway is just a really big slit, you know? And you might be thinking to yourself, well, I don't see weird reflection patterns on my wall, Mark. You're lying to me. Well, yes and no. Okay, so there's clearly an upper limit here to what will cause this interference. So that's what this question is about. What is the given, for a fixed wavelength, for like red light or blue light or violet light or what have you, what is the maximum slit width that will produce no diffraction minimum? No diffraction minimum means there's no shadow, which means it's just bright, which means it's just a window, right? Or it's just a doorway. That's what it means. To have no diffraction minimum means there's no dark spots, it's just all bright and you're just letting all the light through. So what does that mean? That means if we say this is large, which is kind of what the question's asking about, how large does this have to be? They're saying that there is no minimum. Well, if there's no minimum, then we say the dark spot happens at infinity. It happens infinitely far up. There's no dark spot. It happens way, way, way up there. Well, what would the angle be then for really, really far up there? Really, really, really far up there. Don't forget the angle theta that we're measuring. Oh, did I pass it? Yeah, here. Boop, boop, boop. So here they're sort of aiming for that spot right there. If you're aiming for a spot, way up here, then those lines would look like that, right? And you would connect these. You would connect these here to make an isosceles triangle, and then your path difference would be there. So if your point is at an infinite distance away, infinitely far up there, what would that angle be? What would that theta value be? And the answer is, it's a limit, obviously, because it doesn't exist in real life. The answer would be let me just do this here for you. If those are the same, here is your path difference, and this would be your theta value. If that point shoots up to infinity, then theta value approaches 90 degrees. So we can use that fact to reverse engineer what the slit width would have to be. So we would say for a given wavelength lambda, what would there have to be no diffraction minimum? So we would look for a minimum value. So d sine theta equals 1/2 lambda. Okay, and this is where we're saying m is equal to 0 here. M equals 0 because we are looking for the first dark spot. Of course, the first dark spot doesn't exist. So m equals 0 because that's when lambda is, or that's when the path difference is lambda over 2. And then we set theta to be 90 degrees, which makes sine of theta equal to 1. So then you end up getting d equals 1/2 lambda, meaning the largest width that you can make to still see a diffraction pattern is 1/2 of the wavelength. That's pretty small because the wavelength of light is on the order of magnitude of nanometers. That's pretty small. Nano is times 10 to the minus 9. So red light, for instance, is 700 nanometers. So this is saying you need a slit width that is less than 350 nanometers wide. That's pretty small. And anything beyond 350 nanometers wide, you're not going to see any interference patterns. So anything that you can normally see with your naked eye, like a doorway or a window, even your hair. I think your hair is thicker than that as well. So we don't really see this sort of phenomenon happening in our day-to-day lives on accident, because very few things that we interact with on a day-to-day basis are on the order of magnitude of 300 nanometers, right? So this is small. This is on the order of magnitude of 300 nanometers, which is incredibly small. So that sort of explains kind of how and why we don't really see that. Okay, let's do, well, we'll do that question in just a second. Maybe we'll do it first thing tomorrow, but before we do it, I want to introduce a new term for you before we do that example. So we can now talk about fringe numbers. The fringe numbers are the number of bright spots that occur, or the dark spot. So for instance, we can say the central bright spot is the 0th bright spot. It happens, bam, dead center. And then it goes bright and then dark and then bright. So the first bright spot that we see, that is not the central bright spot, we call that the first fringe. Fringe meaning, I mean, in English, the word fringe means kind of like edge case, kind of out over here on the side. So it's the first fringe. It's the first bright spot that happens kind of over here on the side. It's not the first bright spot. The first bright spot is the center, but it's the first fringe. Okay, so we label these with the M values. So M equals 1 would be the first bright fringe. Now, if you look at the dark spots, however, the first dark fringe does not happen at the middle. The first dark fringe happens, again, on the side. And we say the first dark fringe actually occurs when M is equal to 0. Because don't forget, this is M plus a half lambda. So when M is equal to 0, you have lambda over 2, which is your half a wavelength out of phase. So that's going to be a dark spot. So your first dark fringe happens when M is equal to 0, and your first bright fringe happens when M is equal to 1. So we're introducing this sort of notion of fringes. So we'll do this example. Tomorrow at the beginning of lecture. Not tomorrow, Tuesday, because today's Thursday. So we'll do this on as a refresher for Tuesday's lecture. But when we talk about fringe numbers here, that's going to be how many, whether it be a dark fringe or a bright fringe. That's how many peaks there are to one side of the center. So this is a proxy, I guess is what I'm saying. The fringe and the number here is a proxy for the M value. If you know something about the fourth fringe or the third fringe, that inherently tells you the value for M. Okay, so we're well on our way to the wave nature of light. We've introduced sort of interference of light. We've introduced one example of how this happens with Young's double slit experiment. And we have a few equations for Young's double slit experiment. We have two of them. We have one that quantifies the dark spots. We've got one that quantifies the bright spots. And we've introduced the notion of path difference. So we're well on our way to do it, and we'll resume our talks about wave nature of light on Tuesday. So have a good weekend, guys. And just a reminder, your test is tomorrow morning at 8 in the morning. So please make sure you get a good night's rest for that, so you're all well rested and ready to go tomorrow morning. If you're watching on YouTube, I will see you in the next video. Ciao for now.